Hello to everyone. Welcome to the Smart Grid Summit 2023 by Somme Technical University Electrical Engineering Club. This summit is an international online conference streamed right now on our YouTube channel, featuring 6 leading speakers in the field of smart grids. And to give her opening speech, I present to you Somme Technical University Electric and Electronic Faculty, Head of the Electrical Engineering Department, Honorable Professor Belgin Emre Türkay.
Merhaba Azam.
Merhaba.
Şimdi başlıyor değil mi?
Tabii, buyurun hocam.
Tamam. Hello, welcome to our Smart Grid activity. I highly thanks all participants to accept my students' invitation. I know they are so excited since you participate in their organization. They are so lucky to have a chance to listen to valuable experts like you. Let's speak in Turkish. Hepinize hoş geldiniz demek istiyorum. Bu gerçekten Smart Grid akıllı şebekeler etkinliğimizin 4.'sü. Akıllı şebekeler etkinliğini 4 senedir kuruyoruz. Hatta en son kurguladığımız etkinliklerden bir tanesi. Ve bu şekilde online olunca yüz yüze etkinlik yapmanın faydaları çok fazla. Bir arada oluyoruz, sosyal etkinlikler gerçekleştiriyoruz ama online olunca da birkaç kez bunu yapabilme şansımız oldu. Uluslararası bu konuda uzman ekspertleri çağırıp onların fikirlerini almak, onlarla fikir alışverişi yapmak çok faydalı oluyor. En başta kendimizin hangi noktada olduğunu görüyoruz. Sonra onlar hangi konularda çalışıyor, nelerin üzerinde duruyor, bunları görme şansımız oluyor. Aslında pandemi döneminde de uluslararası online bir etkinlik düzenlemiştik. Burada da online olduğu için uluslararası yapma şansını elde edebildik. Şimdi gerçekten bugün çoğu SİGRE'den olmak üzere katılımcılarımız çok değerli, ülkelerinde büyük projeler yürüten, akademisyen ama aynı zamanda sanayi ağırlıklı, şebeke ağırlıklı projeler yürüten değerli kişileri dinleme şansımız olacak. Bence bu etkinlikten maksimum düzeyde faydalanmanız gerekir. Yani böyle bir fırsatı her zaman bulamazsınız. Bazen şansımız olabilir. Belki arkadaşları tek tek buraya getirme şansım olabilir ama hepsini bir arada bulma şansımız her zaman olmayabilir. Bu fırsatı kaçırmamanızı, dikkatle dinlemenizi tavsiye ederim. Hepimize güzel bir etkinlik olsun dilerim.
Teşekkür ederiz hocam. We thank Mrs. Türkay for her speech, and our summit begins with NC SİGRE Kosovo Chairperson, SİGRE Women in Energy Awardee 2022, Pranvera Dobruna Kretsiu, and her speech about interoperability functions for battery energy storage for systems. Hi, welcome. We can't hear your voice right now.
Can you hear me?
Yes. Let me introduce you again. Today we are with NC Tigre Kosovo Chairperson, Tigre Women
Yes.
in Energy Award 2022. Pardon my pronunciation, Pranvera Dobruna Kritiu, and her
Yes.
speech about interoperability functions for battery energy and storage systems.
Yes.
And welcome. I think you can share your screen now, or
No,
you
I'll
can
be
start.
only speaking.
Okay,
Yeah.
we are listening.
Yeah. Just tell me when, and then I will start.
I believe you can start now.
I can start now. Okay. I was very honored to be invited to speak to energy professionals, researchers, and students to discuss the latest trends and advancement in smart technology. Talking about the latest trends in smart technology is a call for more research and development, because the world that is emerging from the renewable, the new energy sources within the energy transition will be very different from the one built on a foundation of the fossil fuel. Yes, we need to drive energy transition forward quickly and with an open approach to technologies, including renewable, low carbon electricity, as well as hydrogen. But the fast integration of the intermittent variable renewable energy sources and the need for more energy storage technologies, which will balance the intermittency to store the surplus of energy and the need to talk to the grid, is becoming an increasingly important topic that needs a special attention. Whether we call it energy transition, maybe you are reading a lot of documents, sometimes it's called energy transition, or the decarbonization process, or the net zero initiative. One thing is common: it should be done through digitalization. It's a must. IT, information technology, and information and communication technology, ICT, are the key enablers for replacing fossil-based power generation with renewables. ICT is a diverse set of technological tools and resources used to transmit, store, create, share, and exchange information. The main application areas of ICT in power system today are energy tariffing and trading, grid planning, automation and control, grid integration of renewable and electric mobility, energy management, electrical protection, cybersecurity, many database applications, such as predictive maintenance. In all these areas, significant research and development efforts are taking place and will have to take place by you, our dear students. In addition, the information technology is increasingly being deployed on distribution grid. These devices can be an important enabling part of the emerging grid of the future. However, what is missing is the ability for all these devices to coordinate and communicate their operation with the grid, and among themselves in a common language, an open standard, and interoperability. Interoperability is, by definition, ability of different systems to work together and communicate, while open standards are only technical standards that are developed and maintained by the standard organizations and made available to the public, possibly on a royalty-free basis. We are seeing every day that the combination of solar and energy storage technologies can generate additional value when interoperable grid support, when we add advanced grid functions for that will allow for intelligent control. Otherwise, it will not be possible, because the solar energy is intermittent, is not base load during the whole day, and energy storage technologies will have to follow the solar and energy production and store the excess energy when the system doesn't need it. That's why we need advanced grid to understand, to talk between parts of the grid. The ability of these devices to respond to command signals will help support distribution grid operation and even sometimes avoid costly grid reinforcement, because we are every day seeing that grid is not properly advanced and designed for all these new devices added into the network. That's why we need sometimes grid enforcement. But if the communication is right and interoperability is properly addressed, then we don't need very expensive grid enforcements. Furthermore, the widespread adoption of these functions could allow energy storage to remove some of the barriers to high penetration that solar energy can produce during the day when we don't need electricity. During the daytime, for example, when the consumption is low and the production of solar is high, then we need to balance, the supply with the production. And the energy storage is enabling this. So the excess electricity will be stored and then it will be used when we need. But everything goes to the possibility that ICT does the work. The units talk between themselves. We also need certification protocols that will enable advanced interoperable energy storage system covering this range of capabilities to better support photovoltaic and renewable energy integration. Otherwise, if we just add solar energy and as well as wind energy to the system without being able to store it when we don't need, then we'll have to shut down solar or wind. And we need more solar and wind. We don't need to shut down them, but we need to find a way that this energy is being used properly and when we need. There are many benefits of interoperability, and when the interoperability is being addressed properly, then it goes further towards the affordability and reliability of the power systems. The power system is reliable when the whole electricity grid is addressed properly. Interoperability means things work together in expected ways. So our expectations are that all parts of the system, adding smart grids, adding all renewables, and having all grid infrastructure work together in expected ways. Yes, we need a lot of investments, but we need a lot of policies that will direct investments in a direct way. We see every day that there are so many backbones of our energy supply. It's becoming the distribution infrastructure. Why? Because as a result of connection of the wide diversity of elements to the power generation with their many, many applications. It's a backbone that will come under massive pressure if we constantly push ahead with the necessary expansion of renewable and thus drastically shift the previous parameters of power transmission distribution as we used to have. We used to have baseload energy, and the energy that was produced was also consumed. Now it's a new era, it's a new transition, and we need to think how to produce and store electricity and use it whenever we need. There are so many case studies where open operability standard for customer devices will improve the operation of the grids. We need more research investment and to advance an open interoperability standard, thereby reduce the cost to install, integrate, operate, upgrade, and maintain smart devices in the distribution grid and overall system. The technical aspects of interoperability has to be extensively discussed. We need to discuss more and more with students, with the researchers, and interoperable solution has to be found. Interoperability has received less attention in the electricity sector before the fast development of renewable. We used IT where it wasn't necessary for efficiency and safety. Now, interoperability is one of the center parts of making the twin digital and green transition a reality. And it's a must to highlight once more, it's a twin digital, green, and transition reality. Interoperability has a sector-specific role in strengthening the internal energy market. Interoperable arrangements for smart metering can contribute to the smart energy consumption. Have you heard about the smart energy consumption? It's the way how the consumption is using communication and ICT technology to adapt to the new system. Interoperability has a cross-sectoral enabling function for a future citizen-centered decarbonization and data-driven energy system. You are aware that the transition will not succeed if the citizens' acceptance is not there. And if we want to have citizens' acceptance, we need to treat them as a part of the transition. And so they need to have enough data, and we need to have a citizen-centered decarbonization so the transition will succeed. Customers need to know what are the new technologies, what are the opportunities the new technologies bring, what is the importance of the smart grid in the decarbonization process, and all these things that are coming every day and putting pressure on the system. Innovative energy services, including demand-side flexibility, can come from other ecosystems closely related to smart metering, such as electromobility in buildings. Data relevant for the creation of such services has to be accessible by final customers and other parties on their behalf. We may use one analog thing in the industry. For example, USB standard was developed in 1990s, and that it allows simple plug-in play between smartphones, tablets, computers, chargers, printers, games, and many other peripheral devices, whose extent has greatly expanded both the usability and types of these personal electronic devices. Also part of the energy system, a smart grid that is added to the distribution network need a simple plug and play devices that are recognizable by other parts of the system. The other case study is the computer mouse. The computer mouse or a smartphone can help us, recognize, for example, in a car Bluetooth system everywhere. So this is like open standard and operability when the smart grid is ready for everybody. It's there. Therefore, interoperability for smart metering effectively requires a policy change to facilitate the full interoperability of the energy services. Why we need policy changes? Because within the transition, we need to recognize that they have to meet other policies to make everything more close to the last citizens, to the customers. And this requirement has to be non-discriminatory and transparent procedures for access to metering and consumption data, and data requires for customers switching demand response and other services, which means that if you have at home a smart meter, that smart meter will try to enable you to have lower electricity bill because you use electricity during the time when there is excess electricity. Then then the utility will in a way grant you more, it will lower your electricity bill because by using a smart metering, you will get a signal that you can use electricity now because it's a lower tariff. So this is the way how customers are accepting new technologies and are making the use of interoperability of these meters and smart grids that add into the distribution network. How this can be done? Government entities working with industry and other stakeholders should work together to promote open standards that enhance connectivity and interoperability. More investments are needed to advance an open building interoperability standard. Therefore, reduce the cost to install, integrate, operate, upgrade, and maintain smart building devices and systems. So you can imagine if we wouldn't have this open building interoperability standard, then everybody who buys a smart meter will have more expenses to actually adapt their home to accept this smart metering. So that's why we need policies that will be open policies that will be friendly for the customers, will enable them and help them to accept the new technologies in the system. The interoperability is, as I said in the previous session, that ability of different systems, devices, and applications to communicate and work together effectively without requiring complex integration or custom development or custom-made solutions. We need an open approach and interoperable different technologies to seamlessly exchange data and interact with each other, regardless of their specific hardware or software involved. We cannot afford that whoever produces a smart device then request a different software. We have to find a way that the software be accessible for the public. This is particularly important in today's digital landscape, where many organizations rely on multiple systems and applications to support their business operation. Interoperability can improve efficiency, enhance data sharing, and access and promote innovative and competition. Why interoperability is important? It is important because it enables different systems, existing and new, devices, and applications to communicate and work together seamlessly without requiring complex integration or other developments. This leads to more efficient, effective workflow, improved data sharing and access, but better user experiences. Interoperability also promotes innovation and competition, as it allows for the development and integration of new technologies and solutions into existing ecosystem. For example, battery storage applications. Battery storage, I call it as a Swiss Army knife because it does whatever you request or digest. We need to find a way to adapt the adaptability of battery storage power station in different application scenarios to be improved. The large-scale application of energy storage is the power conversion system, the part of the battery storage, and the battery management system need to be connected to the communication network, to the existing communication network. So these parts of the network at the grid has to be interoperable. So we get the maximum use of the existing parts. Also, the communication protocols currently are used tradition in the transmission process-oriented protocols, which only guarantee the accuracy and security of data transmission. We need to improve that. It is difficult to simplify the process of connecting a large amount of intelligent electronic devices to the active distribution network, to the existing distribution network that was developed during last 50 years. And to realize the self-description of interoperability of the devices. We cannot change all the electricity grid distribution. We need to update and upgrade the existing one with a new smart metering, but always taking care of interoperability. With the diversification of distributed energy sources connected to the distribution network, the concept of plug and play has emerged to improve the reliability of distributed energy sources connected to the grid. The concept of plug and play is originally a description of a computer system that can automatically configure its extended version and the other devices it extends. Extending the concept of plug and play to the distribution network means that when distribution equipment is physically connected to the electrical network, the distribution monitoring center can anonymously identify the newly connected equipment, create or update the equipment, self-description information in the system, and supervise the newly connected equipment. It means that if a smart metering is being implemented in one of the houses or big building, the system anonymously identifies and the newly connected equipment create an update and recognize the difference that smart metering is bringing and knows what needs to be done. And then further supervise the newly connected equipment. This is interoperability. So we cannot afford, if one of the smart meters be implemented, connected to the network, then the network needs further enforcement to recognize the newcomers. Once the plug and play of distributed energy and intelligent electronic devices can be realized, the distribution network monitoring system will have a certain degree of scalability and flexibility. It will always also improve the ability to adapt during switching operating states. Sometimes this distribution network monitoring system, we call it SCADA. Sometimes we call it also a monitoring system, but this is a system that will recognize all the new switching meters or smart grid appliances. The real plug and play operation of the battery storage is new. And the whole battery storage technologies, including the energy technology storage, including battery storage, which is widespread, with access to regional power grid, has to improve the adaptability of the battery storage power station in different application scenarios. The common problems existing in the information flow of battery storage power station connected to the regional power grid should further be studied, because for the moment we don't have higher capacity of battery storage. The highest battery storage at the moment are 200 or 300 megawatts installed capacities with several hours of megawatt hours. But the large amount and utility scale batteries and their link to the regional network has to be studied, because we need to focus on self-discovery technology, interoperability technology of information interface devices between the region. Many studies are ongoing and many studies has to be conducted, because every day we are seeing new technologies, we are seeing new smart grid applications, and that these application has to be studied adaptable to the existing system. The studies on the plug and play energy flow level implementation technology, information flow level information technology, and grid connected information interaction mechanism are studied, but there are still many key technical problems and difficult to be solved. And this is something that researchers and you, dear students, have to take into consideration, that the energy transition with all these adding all these technologies will very soon have a lot of bottlenecks that has to be addressed. We will see very soon the commercial application of the energy storage. For example, the energy storage can be used for peak shaving. It means that if we have a peak at tea time, as we call it, from 6 to 10 o'clock p.m., that if with storing electricity in the battery during the day, we can shift the load for a time when we have more electricity. In many times, these battery storage can be used for emergency backup and various grid services. Residential application includes self-consumption, off-grid homes, and emergency backup. As I said, battery storage, I call it a Swiss Army knife. It does whatever you request and how you design it. As variable wind and solar power continues to displace traditional generation assets, additional resources are needed to control bulk and local power supply. But one highly versatile option for providing frequency voltage stability is to incorporate energy storage system at the distribution level. We'll see every day more and more renewable energy being connected and integrated at the distribution level. But it's a must to have more and more energy storage system to address the balancing issue, and actually to use this energy storage for arbitration, for example, to charge battery storage when electricity is with a lower price, and use it when electricity with a higher price. This is called arbitration. Deployment of these technologies is expected to increase rapidly as time of use pricing and self-consumption requirements become widespread and providing greater financial incentives. This is not very present at the commercial level, at the distribution level for the certain businesses. It will come very soon because everything is moving faster than we ever thought. The standardization of interoperability certification protocols for many grid support functions has to validate the distribution energy resources, operation, and communication within the power system. It's a must. So all these distributed energy resources that are added to the existing distribution network has to communicate with each other. We need more test protocols for evaluating the energy storage system on interoperability and functionality. This is a must also. If interoperability of energy system storage addresses, then we will be in a position to add more and more distributed energy resources with advanced control features to show the hosting capacity by providing voltage support in distribution circuits. It depends whatever we need. Sometimes provide ancillary services and be used for wide area damping. We will very soon see large-scale storage that will be common for renewable energy smoothing, peak shifting, voltage support, while commercial residential scale systems are financially, at the moment, lucrative in many jurisdictions due to the grid codes and other regulations. For instance, electricity prices in some countries are high enough that storing solar energy for use during peak price period has made some energy storage systems cost effectively, but in some countries not. So it depends on the price, whether the battery storage can be charged with electricity with a low price, then discharged when it needs with electricity with high price, depends on the price of each country. The diversification of distributed energy resources and new models of customers' engagement have added significant complexity to distribution network. We would all like to have, like PVs on the floor. We'll all like to have all smart grid in the house. We'll all like to have a battery storage next to these PVs, but it's something that will come when the distribution network will be ready. We cannot say that we will do it today, and we cannot say that the energy transition is a very easy process and it's not costly. It will be costly, but we need to actually transform the whole sector in order to enable newcomers of renewable and smart grid. Let's say, for example, let's close eyes for a moment and consider a household that has an electric vehicle and charger, rooftop solar panel, an energy storage system in the garage, a smart thermostat, and an advanced meter providing communication between these devices and the utility, and heat pumps and other heating systems. With these devices, interoperability intelligently, solar generation is directed to EV charging and store during times of high production and low cost. When the sun sets, stored energy is used to meet increased load. reducing stress on the grid, and maintaining comfort and convenience for the customer. If you just imagine so many newcomers in the building, so many communication, so many smart grids, then you can imagine what the communication is needed between parts of the sector, how interoperability will enable this, because no building will add everything at one time. For example, start with solar panels on the rooftop, then next year, after 6 months, you add electric vehicle charger, then it should operate with the existing one. Then you add some advanced metering that it should it be interoperable. So you cannot add all these devices and applications at one time. But when you add, the network has to be ready. What can we say about the smart grid? It's an electricity network that uses digital and other advanced technologies to monitor and manage the transport of electricity from all generated resources, existing and new, to meet the varying electricity demand to the end user. Many of these new and disruptive technologies use proprietary interface, and as a result, they do not yet interoperate in some cases. Solar energy is booming, but sometimes we don't know whether the grid is ready. And in some cases, for example, latest information are that some energy companies were forced to unplug hundreds of solar panels after they generate more power than the grid could handle. To protect the grid, sometimes you have to switch off because you have to protect the grid. And it is approved that inadequate power storage systems are not designed. We need more power storage system to avoid to avoid that the renewable energy has to be unplugged. This is something that we are still learning, because at the moment we just added more renewable, we added all applications, but sometimes we see that the network or the grid at the transmission and distribution network was not ready. That's why we need more power storage technologies, including battery storage or pump storages, where the water is being kept as energy to balance the system, to balance the supply and demand. We have to think how to defer expensive grid infrastructure investment. That's why we need smart metering and smart investments and smart consumption. This is something that only interoperability of the existing system with the new parts can enable. Thank you for listening, and I'm ready for your questions. Thank you.
Yeah, we're gonna have questions from the chat too, I suppose, but I just wanna start asking questions myself. Implementing the developments in smart grids regarding high voltage may take some time. How long do you think it would take?
Well, usually these high voltage systems have the long-term expansion planning. And as you may see, we are experiencing that all the countries are updating these investment portfolios and investment plans, because they see that the solar energy and wind energy is being implemented more quickly than we thought. So we believe that there will be many bottlenecks in each countries and interconnection between countries, but there are so many associations and legal bodies that are dealing with this. And we have new standards that will enable resilience of the power network, and that includes also the new network enforcement and the new lines. So not every country will have extra expenses for the network enforcement. It is being done at the regional level because the market functions in that way. But
Thank you.
how long nobody knows. But if the network expansion plan is 220 to 30, usually for 10 years, it means from now until 2030, all these bottlenecks will have to be solved.
How long does it take for the installation cost to pay for itself?
Rate of return for renewable is very low and is becoming very low, while for the network infrastructure is pretty high. But depends on the power flow. For network, for solar, for example, the rate of return is 12 years. That's why they used to have this feed-in tariffs for 12 years. But for the network, for high voltage metering is something like 10 years, but depends on the power flow. Depends how energy flow can pay for the investments. So this is the rate of return.
Will there be a new battery production? Do you see the current battery types as sufficient for storage? Or like if it is sufficient, how can we minimize the areas that needs to be used? Well,
it's a very nice question. 5 years ago, so we are 2023 to 18, I was surprised when many people had a bit of reserves for battery storage. And by that time, we were proposing a hybrid solution. And we wanted to ask all the investors who invest in renewable energy to match a certain capacity with battery storage as well. So this is something that will help them and reduce this bureaucracy, because the whole implementation of this renewable takes time, the bureaucracy to get licenses. So by that time, we thought that it will be a nice approach. But now we may see that some of the countries has adopted that they're offering existing investors who has invested in solar and wind to match their capacity with battery storage, because we are seeing it's a must. Why paying for the balancing when they can invest in battery storage? And the battery storage does a lot of activities. Depends what activities a country wants, on whether primary, secondary regulation, whether black start, whether ancillary services, or be used as arbitration, actually be charged when electricity is cheap and discharged when electricity is expensive. So it's a Swiss Army knife, I say. Whatever you want, they do.
We have also a special question from one of our friends, and it says you were a woman in energy awardee, and you are already a successful woman in energy and electric sector. And I myself am a woman in electrical engineering. What do you think, and are you hopeful about women's presence in electric sector?
But I believe that energy transition is a process that should be used by women. Why? Because I was CEO at the power company producing electricity from coal. But that time, everybody was saying the electricity sector is man-dominated because coal is dirty. Now, renewable energy is clean. That's why we need to use this opportunity to develop renewable energy, because it's clean, it's more women-oriented, it's not only man-oriented. And we see every day more and more women working in the energy sector and working with renewable energy, which is clean. That's why somehow it's an open window for women. Energy transition and renewable is open window for women, and we need to use it.
Mrs. Dobrina, thank you for being here us today. It was a pleasure listening to you.
Thank you so much. I enjoyed talking to the students and researchers. Hope to see you when I'll be in Turkey.
We all hope so too. We will love to see you.
We're organizing a big CERS conference, very big CERS conference, and we'll be in Turkey in October. Thank you so much for organizing.
We can wait to see you.
Thank you.
Dear participants, our summit will continue at 3 p.m. with our other special people in smart grid sector.
Thank you.
Hello, Mr. Pompili. Can you hear us?
Okay, my microphone was off, now it's on. My cam is on too. So, good
Hi.
morning.
Good morning. Let me introduce you. We are continuing our Smart Grid Summit, and I would like to present Massimo Pompili, a full professor in high voltage electrical power system at University of Rome, to talk about natural ester distribution transformers.
Thank you. Thank you very much. How many people we have with us
I think,
attending my presentation, just to know?
yes.
Okay, can you see my screen?
Yes, we can.
Okay. So good morning, everybody. So as Azar said, I'm Massimo Pompili, and I'm with the University of Roma, La Sapienza. University of Roma, La Sapienza, I knew that some of you come from Italy, so you should know La Sapienza, but anyhow, La Sapienza University is the largest public university in Europe and the second in the world. We have more than 110,000 students in different fields, of course. And I am also the IC TC10 secretary. IC, it means International Electrotechnical Commission, and TC10 is for electrical insulation, and in particular for insulating fluid. I am the secretary of this committee. I am also quite active in SIGRE environment, and I'm very happy to be here with all of you. Thanks our cooperation that we have with the Turkish friends, because we are in the same regional group of SIGRE. The name of this group of SIGRE is SERC, Southeast European Regional Group of SIGRE, and is a very, very large group of SIGRE. So the topic of today is the use of natural ester liquid in electrical transformer. For more than 1 century, we used and we are still using mineral oil as the main insulation in the transformer, but in the last 2 decades, we started to use also natural ester. So part of this presentation, the first slides, come thanks to Cargill. Cargill is a global company, is from the United States, but is an international company. And because they are the main producer of these ester liquids. Also, I will present, we create in Italy, then at international level, a working group, to better know the behavior, the fire behavior and the environmental behavior of natural ester. And at an Italian level, it was part of this group. It was my university, the main stakeholder of the sector, like the Italian TSO. It means the name of Italian TSO is Terna, and also a local distributor. Among them, it was also Enel. Enel is also is a global, is the main Italian distributor. And international level, we create a group. The name of this working group, it was D168, and it was a group of SIGRE group. And our task, our goal for this working group is to complete a technical brochure, which will be ready by the end of this year. Indeed, that it is the technical brochure. We assume it to be ready 2 years ago, but due to the pandemic situation, it was not easy to meet here and there, so we are 2 years late, as for several other activities due to the COVID pandemic period. Also, and inside that is the Italian international group, we performed simulation tests comparing the behavior of mineral oil and natural ester transformer. So I will go quite fast for the first slide because I should have 45 minutes, so no so much time. And but then maybe some question will come from you. So some very simple question: where do natural ester come from, and what do they do? So natural ester, as the name is saying, is and in particular, this slide is prepared by the producer Cargill, and the commercial name of natural ester produced by Cargill, it is Environment FR3. They are vegetable oil based. Nothing new under the sun. The first application, because indeed they are very simple products like soybean or similar, and the first transformer trying to use vegetable oil, these experimental transformers were built at the beginning of the last century. It means now about 100 years ago. But they have a big problem: oxidation stability, because natural ester are like olive oil. They are very good for several applications, but when they are in contact with oxygen, and the oxygen is in there, they start to age. It means that oxidation started to be active, and after oxidation they change the property, and in a very short time they were not more able to be used as insulating liquid, because with the oxidation, when this oxidation process, the natural ester liquid started to lose the good property of viscosity, and so they become more or less like wax. So the circulation is not more easy in the transformer. The first producer in the world, indeed, he reported the first at the commercial level. It was the commercial production started in 1991 by Cooper and then Cargill. They are in the same group, but also we knew that before that 1991, it was some producer, especially in Eastern Europe, trying to use natural ester liquid in transformer. Of course, the main scope of this application, it was to try a way to replace mineral oils, which are petroleum-based liquid. So we may have. I am no a good chemistry, so I know chemistry, but I am not a good teacher for chemistry. They may come from different bean, like soybean, but also other different plants. Of course, having different properties in terms of both viscosity, using different plants, and also different pull point and flash point. In some cases, and in general, we are not using pure soybean, but they are blends of different beans to use it to produce this natural ester liquid. Of course, different producer, and we have at least other two big one, like M&I material and insulation from UK in Manchester. They are a large producer of natural ester. And also we have a third big producer in Italy, which is Fratelli Parodi. This was a photograph of the market up to 10 years ago. Now, at the moment, it is here, and we know that several producers coming from China, India, started in the production of natural ester liquid. So at the moment, it is not easy to say how many producers we have around the world. And anyway, at the moment, the main producers are for us as a reference, Cargill, M&I, Cargill American, M&I from United States, and Fratelli Parodi is from Italy. So when we speak is where is soybean come from different parts of the world according to the price. So at the moment the production of soybean is more coming from South Africa, but also from the past from Brazil and other countries. So is the first point is we lasted over 50 years to prove stability at aging for natural ester, and this was made making different tests, long-term tests for natural ester used in transformer. Is here in the slides I presented for you the main test tested, which you can find some reference in some bibliography. So it was what happened on the internal breakdown, internal arc. This is very important because it means that the molecular breaks and they change completely. So you may produce different substances. Then is the long-term accelerated aging. According to we have a standard in the United States, IEEE C 57.100. This is not important, but anyway, it's a long-term accelerated test. Then we have aging evaluation with free breathing transformer, and this study was lasted for more than 10 years. It means experimental transformer were put in service, and then we studied along the time what did happen. We took some sample from this transformer and we measure the oxidation stability, the tan delta, and other properties. Then there are reported in bibliography other tests. High temperature operation lasted for more than 6 years, and then other. So it means as you may see, is a long story. This is what already happened in our field, in the field of electrical engineer. They don't want to change so much, and when they need to change something, they really want to be sure that the changement which we are making is good for the system without introducing some unexpected problem. So chemistry, we can skip some chemistry. So how it is insulating liquid are produced. Anyway, but this is a very important. This is the result. Is the comparison between. This is a test quite common to measure how the oil activate aging in paper. So the test was prolonged for from 100 and 100 of years, from left to right. The first box, you have 500 hours, and the impregnated paper, both paper impregnated with the natural ester, here called FR3 fluid, and the mineral oil. It was it remained in under an oven for 500 hours at 170 degrees. It's clear how the changement, how the color is different for natural ester and mineral oil. The second box is after 1,000 hours, same temperature, and the comparison is again between natural ester liquid and mineral oil, and you can see that this paper with mineral oil, leaving in contact with the mineral oil for more than 40 days, 1,000 hours, it became practically black. The third box is 2,000 hours. You can see the difference. The papers really, in the case of mineral oil, did break, so it means it's no more consistent. And the last one, the paper is completely destroyed by the oil. It is only for mineral oil, but not for in natural ester liquid. So at the moment we can say that at the oxidation stability, the performance of natural ester liquid maybe are similar or even better than mineral oil. Is important also because, as we will see later, this insulated liquid may work at a higher temperature. They belong to different thermal classes. So we have I put a circle in red. You can see that according to in the first line is for mineral oil and kraft paper. It means that the thermal index is 95 degrees and the thermal class is 105. And natural ester liquid and kraft paper, the thermal class is 120. It means that your transformer may work at a higher temperature. It means that you can load it much more your transformer. You can overpass some moment when your system need to be overloaded. So I can see environmental aspects, very simple. We come back on this point later. First is we can say as at the beginning that FR3 and in general natural ester liquid are sustainable because soybeans use CO2 from air. So this is very important, especially in the study of the life cycle assessment. So this is the result of one study reported made in United States by the NIST. NIST in the United States is the National Institute of Standard Technology, which is in Washington, D.C. And in gray, you have the quantity of CO2 needed for the production of 1 liter of mineral oil, and in green, the similar for the natural ester. So the first part is raw materials. Raw materials, natural mineral oil, you need to produce for the extraction of the oil, you need to consume CO2. In the case of natural ester or soybean, is this balance is positive because the CO2 is extracted from air because due to the you know from science how the plants works in front of air and CO2. Then is a comparison for other part of the life of the transformer, manufacturing, transportation, use, end of life, and the sum is totally in favor of natural ester liquid. So also from life cycle assessment, CO2 footprint, we may have one conclusion that this is favorable for in the case of use of natural ester liquid. Another good point for natural ester. We have 4 line, but please check better the in blue. We have a mineral oil, and then we have in the triangle in green. So we need, and then we can compare other liquid. But if you compare the green line, which is natural ester liquid, with the blue line, which is for mineral oil, and this curve gives biodegradation of the liquid in soil. And according to international legislation or rules, you say that substances are biodegradable when they are destroyed more than 95% in less than 28 days. So we have to look at the line between the gray region and the white region. You can say that for natural ester, you arrive in 28 days. In 28 days, you arrive at more or less 95% of biodegradability. And for mineral oil, the conclusion are completely different, because after 28 days, only the 20% of the liquid is naturally destroyed by nature. Okay. I don't want to boring you with different certificate that this liquid have had around the world. So we come back to the American guide C57 because it's quite important, and also because the report is standard report environmental study made by EPA, and EPA is very important association in or agency in the United States. EPA means Environmental Protection Agency. You know that all the products which are used in the United States before to enter in the market, they are under control of this agency to check, to control if they are dangerous for humans or for environment. Okay, our win now is fire safety. Is another important point. Is okay. Is a comparison of we have three liquid. In this case, we have mineral oil in the left side of the graph. Then in the right side of the graph is natural ester, and in between we have synthetic ester. Synthetic ester are ester. There are not so much difference between natural and synthetic ester. Indeed, both of them are made in lab due to by the chemistry industry. But in this case, we are not using soybean, but we are using chemical substances to produce the final products. And the comparison is also we compared both flash point and fire point, and you can see that mineral oil is very important to look at the flash point. The flash point is the temperature at which the the vapor of the liquid started to burn. And you can see that flash point, if you look at the left side of this graph, you can see that mineral oil flash point is something like 150. And if you look at the flash point of natural ester, we have more than 300 degrees. So more than double. It means that the risk of fire using natural ester is really lower. So this is important for different reasons. First, one of the reasons is reduction of the risk. And against this risk, of course, we have international and local rules which give distance clearance of respect between two units, or in the case for instance, you can check in the number in black, in bold. So it is a two-column minimum separation distance from transformer to buildings. And in case of mineral oil, which are in class O, this distance is a function of the volume of the oil in liter, and it is for a very quite large transformer, more than 20,000 liters, this distance may arrive at more than 15 meters in case of no flammable buildings, so it's a very large distance. In the case of natural ester, like FR3, I remember is a natural ester that we are considering, which is in class K. This distance is reduced up to 4.6 meters. It means more than 3 times less. So it's very important reduction in your substation, especially in the case when your substation is close to the city, is close to downtown, you have no space to create or to build up a new substation where you want to put some transformer. I will say something more, because as a Roma University, we participate at the replacement of many transformers in Rio de Janeiro before the Olympic game, and that some action in Rio de Janeiro was possible also because we used the transformer insulated with the natural ester. Otherwise, the distance between one transformer and other buildings had to be too much. Okay, this slide is in Portuguese because come from my study that we made in Rio de Janeiro for the Olympic game in the year 2016, if I remember well. And so you have, you may have also visually how this reduction may be reduced. Left side, you have the situation in case of mineral oil, and in green, in the right side of the slides, you will have the situation in case of natural ester transformer. Here, there are no numbers because the number depends on the quantity of mineral oil which you are using in your transformer. I don't want to enter into this requirement present in some standard. You can go ahead. Okay. Okay, before I told you that we have international rules, but we have also local rules. In Italy, we have our own rules concerning safety protection when you are using you are positioning a transformer. You have to respect some local rules. For sure, in Turkey you have your rules. You presented some rules for I don't remember which country, but we have both international reference and the local reference, which are different around the world. And okay, we can go ahead. Standard. Also, I am sure that you know IC. I told you IC is International Electrical Commission, and this standard they have a code. The standard IC 62770 is the standard for giving the main properties for natural ester liquid. So we can leave together some number, of course, and is reporting the standard how the which are the property which is new into mineral new natural ester have to have before to make possible to use them in electrical transformer. Of course, the appearance must be clear. You cannot use the dark oxidated oil, of course. Kinematic viscosity. I know that not all of you are electrical engineers, so it's a very important property because to the viscosity is liquid having different viscosity. The way in which the heat is transferred is completely different. So we are looking for with insulated liquid having quite a low viscosity. So for this reason, the standard IC 62770, which are quite identical to American standard produced by STM, gives this reference at 100 degrees. The viscosity must be lower than 15 centistop or millimeter square share by second by centimeter square. And of course, the standard report is number for two different temperatures, at 100 degrees or 90 degrees and 40 degrees. And of course, we are looking with much more interest the performance of kinematic viscosity at higher temperature, when it's much important to exchange it with because we have to remove the heating from the transformer. Then we have pull point. Pull point is the temperature related to very low temperature. Is the limit at which you can still use the liquid, because otherwise the liquid, especially the oil, started to become similar to wax, so is no more able to circulate in transformer. Then is a maximum for water content, is some limit for density, so breakdown voltage. Indeed, the breakdown voltage is as measured by a standard IC 60156 is not so important, because this number depends not mainly from the liquid itself, but depends from water dispersion which you have in your liquid. Then is the dissipation factor and other property. And we are okay. It's a focus on this number. Please remember this number: fire point or flash point must be higher than 300 degrees. is very big number, because remember that in transformer, the risk to have a fire is very important. And if you are using a liquid using a very high fire flash point, this risk is reduced. Don't forget for a while that we are using a large quantity of insulating liquid. Just to have a reference at the quantity of the oil, you may assume in the first approximation that for each kilovolt amps, you are using 1 liter of oil. It means that you are using, imagine a transmission transformer of 250 megavolt ampere. It means that you are using something like 200, assuming density is equal to 1 is not true, but anyway, you are assuming that you are using 250 tons of oil. Imagine 25,000 liters of oil. It's very, very big quantity. And this is also for distribution transformer when we are using inside the building. Of course, a lower quantity. Imagine one transformer of the power rate of 400 kilowatt amps. It means that you are using something like 400 liter of insulating liquid, and it is insulating liquid is the products coming from crude, from petroleum. Imagine that when we have a fire, what happened, and I will show you some picture later on. Okay, here is a similar table, but as reported in different standard, because the previous slide, the standard is produced by IC, but IC is not the only international body where we produce standard. There are also other in the world, like in IEEE environment. Also, we produce standard in ISTM environment, also in SIGRE, because SIGRE normally they don't produce standard, but we produce a technical brochure. And in technical brochure, when you are reporting some number, the meaning is more or less a limit which is at least recommended for your use. So this is the case that I told you is the case of Rio de Janeiro. So it means that just to have an idea of the importance of the transformer in Rio de Janeiro. The number of distribution transformers is an estimation. Nobody knows this number. The number of distribution transformers only in the city of the Rio de Janeiro is more than 1 million units. So a very big number. So total power transformer use is in this number is expressed in kilowatt amps. And new medium to large, this is a large transformer, and it means transmission transformer, more than 1,000 transformer, and the last one, retrofilled medium to large power. Retrofilling is a special technique. It was not used everywhere in the world. In some countries, quite used. So it means that when your transformer started to become old, you open your transformer, you remove the insulation. Normally, you remove the insulating liquid, you change the oil, and so giving a new life for your transformer. And changing the oil, you can use, instead of mineral oil, you can use natural ester liquid. Okay, is okay. This is unfortunately it is a video, but my video doesn't work. I am using an Apple computer, and I don't know for some reason. But this is what is happening in the case of fire of a distribution transformer. This is in my city, Roma. You can see that no people died, so not very dangerous. But anyway, imagine one building, all the smoke, black smoke coming out. You can imagine this is downtown in Roma. You can imagine how the people didn't understand what was happening, and the day after it was on the media, on the newspaper, big fire in Roma with some problem and so on. So this is a mediatic impact on the distributor and also transmission system operator is quite important today. So we cannot more accept a situation like this. Because situation like this, it means that something is wrong, that you have even if you have no people died, it means that some risk is present in your building. So we have to take care at the today time. I took some pictures that coming from my collection. This was it was a failure of high voltage bushing in a step transformer. It means in power plant. This time the power nominal rate of the transformer is quite high, 370 megawatt amps. It is a step up transformer, so it means 20 to 410 kilovolt, and the quantity of the oil is 55 tons of mineral oil. This case is well remembered. Why? No people died, so nothing serious really happened. But this fire did happen in a harbor, in a port not far from Roma, and it was during the summer period, and this port is the most used port for all the ships that move from Italy to one of the main islands, Sardinia. So all the people arriving with the ship or departing with the ship they can see something like this. And it was no way to reduce the smoke. Why? Because this black smoke come from very, very small fire inside the transformer, and transformer is closed, and the oil is trapped in the paper. So this oil going on in burning for a long time. This situation remained more or less for 2 or 3 days. So again, all the people, all the media, all the newspaper or television say there's something wrong. What happened? But again, I told you, no people died, but the situation is not today time is not more acceptable. So this was the working group that we set up in Italy to study the possibility to use natural ester instead of mineral oil. It was the participation of my university. It was Italian firefighter authority. It was ISPRA. ISPRA is the Italian Department for Land Protection and Environment. And it was INAIL, it's safety for workers. So we studied for 2 or 3 years, we compared different risks, that which may have using mineral oil or natural ester. We produce also a brochure in Italian, and this brochure now is in part we took this Italian brochure to prepare a SIGRE technical brochure, which will be, which I said you will be published at the end of this year. In English, of course, there are also other contributions, not only from Italy, so by SIGRE. So when I hope that in the future you can read this report. So also in our group we made one study. We did check all the fire which happened in 10 years period, and we discovered that we have more than 5,000 cases of fire involving electrical system and in particular transformer in 10 years. But of these 5,500 cases, only a few of them, only 125, have had a significant relevance. And we split these 192 in two classes. The first class is concerning 142 for big transformer. It means a transmission transformer, and 50 distribution transformer. And among all these big fire, only 14 we could classify as catastrophic. It means with the complete destroyed of the transformer. Again, no people died, so at the end of a conclusion, one conclusion is very important. Don't forget this conclusion, that transformer are really safe equipment, but we have to avoid an unpleasant situation. Is okay? Come back. Okay. Then, as I told you, the project, Italian project, became international project under the name as the D168, and the scope it was to produce this brochure for natural synthetic ester fire and environmental performance. So we compare our study with the other studies made around the world. And so I will show you some tests. We are inside the firefighter laboratory. And okay, this is very interesting pictures. We simulate, this is called, this test is a SPRAI test. Is left side is for natural ester, right side is for mineral oil. So we triggered the fire with external flame. So it was a spray. You can see better here is a spray of the oil preheated. We selected at 50 degrees. And you can see for mineral oil, immediately you have a flame. Then you can remove the external flame, but the flame remain active. So the spray remain on. So it means that when one fire starts in a mineral oil, it's not easy to switch off. Completely different in the case of natural ester. Natural ester, you need, it's not easy to trigger the fire, even if we're using an external fire. For 1 second, the fire remain on, but after 1 second, in 2 seconds, the flame is switched off. So we can conclude that we can say that natural ester have also the property of self. Okay, it's working now. Self-extinguishing property. So fire, in case of an accidental fire, the fire is automatically extinguished thanks to the property, internal property of the. We have to test this. Okay, this video is working. This is a natural ester. You can see the external flame. The operator is triggering the fire. Then is remove the external flame, and the fire stopped. This video, I don't know this is for natural ester. This is the case of mineral oil, but the working the video. Okay, similar experiment. External flame. The operator triggered the fire. Then we removed the external flame, but when you remove the external flame, the fire remains on. Okay. Okay. Also, we simulate another test. That is a distribution transformer. Of course, we started we used two. If you look carefully, there are two transformers. Both are green because we want identical transformer. We fill one transformer with mineral oil and the other with natural ester. So we were simulating a fire. Okay, we were simulating what did happen under an electrical breakdown, an electrical arc. In both cases. So this is the Italian fire laboratory, very large. In the middle, you can see the two transformers. Okay, the conclusion of this test. Okay, is look at the. This is what did happen. So we started to heating the transformer. Okay, we put two probe, one in the upper part of the transformer, and the probe and call it B in the lower part of the transformer. We can have a look, for instance, at the upper part of the transformer. So we can compare the orange line with the green line. Okay, in the case of the green line, we started to heating the oil. Temperature is slowly increasing, prolonging, lasting the heating time. So is heating is going on after 1 hour, but nothing happened. Maximum temperature, it was something like 80 degrees, but no fire, nothing happened. In the case of orange, it's a case of mineral oil for transformer. So again, we started to heating the mineral oil. So we temperature increase up to arrive at this point at 130 degrees. If you remember, this is a fire point of the mineral oil. So it means that the oil started to burn, as you can see here. So this is the case of mineral oil. So we preheated the oil, and we arrive at 130 degrees. And arriving at the temperature after 34 minutes, it means after more or less half an hour, we have the oil started to burn. Okay, then we made also different tests in open vessel, so more contact with air, so making the fire easier. And we had also identical results. The better behavior of fire and better fire performance of natural ester transformer compared with distribution transformer. Okay, this video is going on. This is the left side is okay, is mineral oil. So we are heating the transformer. After 5 minutes, we reach the temperature of 120 degrees. And the left side, this is natural ester, nothing happened. Okay, this is for the case of this is mineral oil. Then mineral oil started to vaporize or to burn, producing a lot of vapor. Okay, we can. Okay,
Mr. Pompili, I'm sorry for interrupting,
yes,
but
I am. Yes, I am on the conclusion. Okay.
Okay.
Just to add, I want to show you the final. Also, we analyzed the smoke because it's very important, the production emission of the smoke. And the results in this case, it was, because I have no more time to tell you more, but the description of the test, it was not easy because we had to collect the smoke, we had to detect, we have put in some special gas chromatography to analyze what was produced in the case of fire in the smoke. So the conclusion is here. So we analyzed different CO, NOx, O2, other toxic organic compounds, and similar. And in all cases, we found a better behavior of natural ester if compared with mineral oil transformer. Okay. So the conclusion should have here somewhere, but the conclusion is that after 10 years, so natural ester and so normally transformers are insulated and you are made using mineral oil. Mineral oil is come from crude. Is a good product, come from, of course, is nature. We have a lot of crude around the world. The price is reasonable, apart the last 2 years, but anyway, the price is reasonable. But crude is flammable, and it means that you are putting your transformer, which you are heating your transformer because you have the losses in the transformer. And this may introduce some risk in your substation. So we, from more than 1 century, we have the idea to use natural ester, but up to the end of the last year, it means at the beginning of 2000, we were not able to use in industrial scale natural ester liquid because the oxidation, their poor oxidation stability. Now we are the industry is capable to produce natural ester much more stable, and so we started to use. At the moment in the world, we are a large number of transformers. We change the technology, we switch technology from the natural ester transformer to natural ester transformer. And we found after more than 10 years as exercise, they are in service. We discovered that they work perfectly without any problem. So we can say that the technology is matter for future, for now and for future. Thank you very much. And so I conclude 5 minutes late, but more or less what I wanted to say to you.
Mr. Pompili, thank you for being with us today. We are so happy to listen to your presentation. And now we will continue with our next guests. They are Brian Berry and Emmanuel Biu, and they will be informing us about dynamic line rating and using digital technology to get more out of line assets.
Thank you very much. Please report to all the audience. If they have some question, they can write to me, and I will have to reply. Thank you, and bye-bye. Bye-bye.
Goodbye. Mr. B and Mr. Biu, can you hear me?
Yeah, I can hear you. And you, is it okay for you? Can you hear me?
Yes, we can.
Okay, that is nice. So, should I start now?
Yes, please. I am right now trying to give you the permission to present.
Okay, I have no slide. I will. I will make a very short introduction before our colleagues Brian will present the dynamic line rating. My short introduction is to introduce this topic, dynamic line rating, with a certain perspective, experience from transmission system operators. So things start, I would say, things like 15 years ago in Western Europe. It's a problem that face many transmission system operators. And so think about energy transition and about having to develop the grid. So when we have to develop the grid, you have to gather a certain number of assumptions. So for example, it's about a load forecast. But it's also about a new generation, coming generation. So when it's about the new generation, three different questions: where, how much, and when. Where? So think about gas generation, for example, CCGT. More or less, you know the place where CCGT will connect in the 5 to 10 years. So you have a certain visibility. How much you can imagine, and probably in general, you get some information from promoters about the number of units they want to install in a certain place. And when you have also a certain perspective, I mean that building a CCGT or coal power plant, things like that, need a certain delay, a certain number of years. That may be 5 years in case of nuclear, for example. In case of ACU, for example, that can be 5, 7, 10 years in advance. So you have this kind of information. Now think about energy transition. And at that moment, 15 years ago, the transmission system operators started to observe a massive request for connection from wind generation. Wind generation, it is very different in terms of grid planning. So now imagine about Turkey, where we have a lot of wind in the west of the country in Ege region. So, but when you talk about where, it's not something very precise. This region is very wide, and there is many different locations for having wind generation. And all those decisions will be taken by individual actors. It is not one unique actor. It is dozens or even more actors who are developing their projects. So you don't have this information as the TSO. That is not precise. Another question is how much. Actually, you don't know exactly how much wind will arrive in Ege region. Is it 3, 5, 7, 10 gigawatts? Now we don't know. That may be even much more in the energy transition, of course. And the last question is when. The problem of when is, of course, you don't know exactly when, but if you want to be sure, if you want to have the very precise information, you will be late. because the time to develop wind generation or solar generation, even more, is very short. That may be 1 year, 2 years, 3 years. So when the time to develop line is much longer, you need more time to develop a line because it is a linear infrastructure. That is the problem. So at that moment, and it is of course still the case, TSOs are facing that kind of challenge. So what is the challenge exactly? Well, when you think about a line over a line, it's a problem of temperature of the cable. More current you have in the line, higher is the temperature of the cable. So you have the problem of dilatation, and then the distance to the ground. Then arrives a very smart idea. Idea is to say, okay, guys, you have a problem with evacuation of wind generation when turbines produce at their maximum. But when they produce at their maximum, it's windy. And the wind is one of the best solutions to cool the temperature of the line. Then actually, you don't have a problem, because when you have to transmit more electricity, it's windy, and then the capacity of the line, the real capacity of the line, it's much higher than what you were thinking before. So that is idea. That is a very smart idea. Now comes the time to implement that idea, and that is much more complex, and Brian will develop that. But just think about how to measure that. What kind of sensor? Should we measure the distance to the ground, and also where? Because the line is dozens of kilometers, 100 kilometers perhaps. So do you have to monitor every part of the line? It's complex. If the line receives wind, but if there is somewhere an obstacle, for example, a forest that blocks the wind, what to imagine? So that is part of the complexity. Modeling is also something that is challenging. So you can think that now we are entering in a question of big data and real time. It's important for dispatching center to know what is the situation today at that perfect moment. So it's real time, but it's also involving forecasting, because the dispatching center need also to know what will be the situation in 1 hour, 2 hours, 3 hours, etc., like that, to be ready to prepare the security of the grid. That is the end of my introduction. Just one very short message to you, to the students. I know you are many to be involved in electric engineering, and so probably very concerned by global warming, and probably wanted to contribute to the energy transition. And that is definitely a good point. So probably you think about working in a solar sector, in wind turbine sector. That is very nice. Perhaps also in hydrogen, green hydrogen, that is very nice. Or perhaps storage or electric mobility. That is very challenging, but also please don't forget the grid. The transmission grid is also part of the energy transition. And joining TSO's transmission system operator is for you a promise for you as engineer, young engineer, for very exciting professional challenges. Thank you. Thank you very much. Hello, Brian.
Great. Thank you very much. I'm going to just share my screen now as well, and hopefully it's going to work perfectly. Let's see. Okay, let's see. I'm hoping that's working. Are you guys able to see a PowerPoint presentation?
Yeah.
Okay, great. Well, yeah, my name's Brian Berry. I'm a chief of product at Ampassimon, which we're going to talk about one of their solutions, dynamic line rating, which Emmanuel spoke about earlier. It's a very interesting technology, both on a technical challenge, but also on a commercial challenge, like what it actually brings to the party. So let's dive straight into that. So what I'm going to do, I will give you a brief overview of who Ampassimon are, just so you know where we come from and who's the company behind this. And then I'll talk a little bit about some of the stuff that Emmanuel was going on about with the capacity constraints. So understanding, maybe with some pictures on, what are the blockages? What's the motivation for dynamic line rating? I'll then go into line rating basics, what people do without dynamic line rating. And then lastly, I'll go into the cool stuff around dynamic line rating and what Empassimon does to really help on this front. All right, so Empassimon is a relatively small to medium-sized company, about 70 employees across 3 countries. So we're based in Liège, Belgium, also Madrid, Spain, and Atlanta in the USA. We've got about 100 active dynamic line rating deployments around the world, and deployments in over 25 countries and 30 plus utilities. So yeah, quite an interesting company. We don't only do dynamic line rating. We've actually got 3 pillars of our organization, which you can see on the left-hand side there. We've got capacity optimization, which is dynamic line rating. We've got asset health monitoring, so cables and overhead lines, understanding their health, how old are these lines and cables, are they in a good shape, are they going to blow up, for example. And then grid reliability, where we talk about helping our utilities keep the lights on fundamentally. So giving them information that allows them to make good decisions in real time. Now, as I say, those 3 pillars are across 2 verticals, and that is overhead lines. So all the overhead lines that you can see, air insulated lines, that's where dynamic line rating comes in. But we also have solutions for underground cables. And underground cables, specifically on asset health, we've got partial discharge monitoring and a lot of cool technologies there. But today I'm going to talk about dynamic line rating, so we'll jump straight into that. Okay, so before we talk about dynamic line rating, let's talk about what Emmanuel was talking about around money and power. Okay, so what I'm showing you here are 2 maps. On the left-hand side, I've got the USA, and on the right-hand side, I've got Europe. Now, the thing is, the electricity price is not fixed. It's all based on markets. And that means that if there is an oversupply, so if there's a lot of generation, but no one wants to buy it, then my price is going to go down. And conversely, if there's a high demand, lots of people want it, but there's not enough supply, my price goes up. This is standard market stuff, okay? Now, not only that, this is locational, right? So I can have a lot of power. I can have power coming from offshore wind, okay? It could be in the middle of the sea, but it's not very useful in the middle of the sea. I've got to transport that power from the middle of the sea to where I'm going to use it, which might be New York City. It might be a big industrial complex, okay? The generation is often not in the same location as where you would use it. And this, through modern market design, we regulate that with price. So what I'm showing you here, those are actually megawatt prices for different regions in the grid in the USA and similarly in Europe. So you can see, for example, BGE, this region for 1 megawatt hour costs $761. Yet if I buy that same megawatt hour in PSEG, that's 67. Okay, it's a tenth of the price. Why? Why am I paying 10 times more in one region? And how do I control this that I don't have to pay so much? Okay, well, it's fundamentally around transmission. I've got power lines that carry the power from where it's generated to where it is consumed. And those power lines can only carry so much power. If I hit the limit, that's the end of that. I can't transport more. So I have an undersupply in the region where I have an over demand, price goes up. And where I have a lot of generation and not a lot of demand, price goes down. Okay, so transmission, as Emmanuel was saying, transmission is the key. How do we get that power from where it's generated to where it's needed? Now, what I want to point you to here is that this is multi-billion dollars per country. So in each country, there's different ways to govern this, but these constraints cost the consumer, and the consumer is you and me. So not big electricity companies, you and I, when we pay our electricity bills, all of these constraints come to us. So when we ask for wind power and when we ask for solar and all of these things, at the end of the day, our electricity bill goes up and up and up and up and up, unless we do some clever things to try keep it down. So talking about transmission lines. Okay, so this is pretty simple. We've got a piece of metal traveling hundreds of kilometers, and we're going to shove some current down it. Okay, nothing fancy. I mean, you can make it fancy. There's a lot of science behind it, but largely it's a piece of metal and we're shoving current down it. Now, at the end of the day, when you shove current down a wire, you get I squared R losses. And I squared R losses heat up that line. Okay. Now, if I heat up that line, similar to the previous presentation, when it starts getting very hot, you start damaging things. So we need to keep this below a certain temperature to make sure that we don't bend that metal, we don't melt the metal, we don't damage the metal. And there's a few energy inputs that can reduce this heating. So the input is you've got solar heating. Oh, don't know why I changed there. Sorry. You've got solar heating, which is from the sun. You've got the current heating, but you've got cooling from wind, and you've got cooling from the ambient temperature. That's the energy input into this line. Now, in utilities for many, many years, you used to be able to buy a power line, and still today, you buy a power line. You say, hey, I want one of them. I want 100 kilometers of this conductor. And when you buy that conductor, you get an instruction manual, and it says, the rating for this is 100 amps or 1,000 amps, and it's based on XYZ. And that's your boilerplate. You can take that and you can operate it like that. But the thing is, that is very conservative. And we call that your static line rating. And basically what that's saying is, you know, we're going to assume that it's the hottest day. It's a very hot temperature. There's no wind. There's no anything else cooling the line. And if you were to run it like that, this is how hot it would get, and then it would be damaged. So that gives you X amount of amps that you can push through the line. But we all know winter's cold, summer's hot. So if I assume something that came from a factory at 30 degrees Celsius, but I'm running this in Norway, which is cold all the time, surely I can push it a bit more. Well, that's where seasonal adjusted rating comes from. So what I do is I work out my typical highest temperature that I would have in winter, the highest temperature I'd have in summer. And basically every year in winter, I push up higher ratings, and in summer I have lower ratings. That's seasonal adjusted. But we can take it one step further. We can use weather providers. So we can take weather information, just like you have on your cell phone, to tell you whether it's safe to go to the beach or not, whether it's going to rain, what temperature it's going to be. We can use that, and we can adjust the line rating based on the ambient temperature that's going to exist. So here you can start to see a daily trend. Sun comes up, sun goes down. But we can take it even one step further than that, and that is by adding all of the above plus wind. Now, the thing is, with wind, you can see there's no longer a trend. There's no longer a day, night. It depends if the wind's blowing. Now, the important thing about this is that wind is actually the biggest contributor of savings. So if I look at all the inputs that can go into a line, I've got ambient temperature. So a 2-degree increase relates to a 2% increase in capacity. 10 degrees Celsius, which is a lot, gives me 11% capacity increase. Solar radiation, so middle of the night versus middle of the day, 18%. Okay, not bad. But cloud shadowing, that can change it. But wind, with 3 feet per second. Now, 3 feet per second is about 1 meter a second, right? That's, if you're walking in the street, you walk at a speed of about 1 meter per second. That's the sort of wind that we're talking about. Very low wind, hardly any wind, actually. Okay. If it's perpendicular to the line, you get plus 44% extra capacity. Massive amounts of what we're saying is you can push 44% more current through that line. So you could have 1.5 power stations with the same line, just if you consider wind. That's huge, right? Huge saving. All right, to make this start getting into data and start exciting some of the engineers in the room. So if you put this onto a chart of statistics, so on this chart, what I'm showing is on the x-axis, I have amount of time in the year. So over here, 1 would be basically 0, hardly any of the time of the year. And on the right-hand side would be 100% of the time. And this is statistically showing me how the rating changes. So static rating, which is on the y-axis, how much rating I have, basically 100% of the time I always use the same rating. But with real-time AAR, ambient adjusted rating, or real-time dynamic line rating, basically some of the percentage of time I can actually get with DLR, I can get actually, maybe 20 to 20% of the time, I can have 50% extra. 50% of the time, I can have another 40%. And 90% of the time, I can have an extra 10 to 20% capacity. Okay, because what this is taking into account is the wind blowing or not blowing, etc. And exactly what Emmanuel was talking about with wind in feed, you can see on this graph here, the blue and the gray. So if you assume the static rating, remember wind doesn't generate, wind power doesn't generate all the time. It only generates when the wind is blowing. Lucky us, that's exactly when we get the most benefit from dynamic line rating. So if we consider dynamic line rating, we can all of a sudden add a whole extra 40% wind hosting capacity for the same price of transmission. Now, bear in mind, why do we care about this? We care about this because if I build lots and lots of power stations, wind power stations and all of that costs a lot of money, but I also have to build the grid. And when we build lines, we're talking about billions of US dollars, billions. And not only lots of money, lots and lots of time. It takes a long time, over 10 years to build lines. So this is huge. So Ampassimon offers 3 solutions here. I'm not here to sell to you. I just use the slide because it's easy to explain. But we can do the ambient adjusted rating. We can do it with weather providers, but we can also do dynamic line rating with sensors on the line. And as I say, going from an ambient adjusted rating can give you plus 15%, 10 to 15%, whereas dynamic line rating with a sensor on the line can give you up to 40% extra. Enough about that. So here's our cool technology. This is a picture of our sensor. Might not look like much. It looks like an aluminium box. Okay. Glad I did engineering for aluminium box. That sounds pretty boring. But inside that box is a lot of electronics. Okay, there's a modem in there. There are 3D accelerometers that has been tested to withstand high voltages. I mean, that thing is going to be sitting on up to 800 kVs. So sitting at an 800 kilovolt line in the middle of the line. So that gets attached to the line. And one of the things that we're doing is we're measuring the vibration inside this box. Now you might be sitting there thinking, Brian, you were talking about wind, you're talking about temperature, you're talking about current, and now you're telling me you measure vibration. What on earth are you talking about? That just doesn't make any sense. Well, vibration is at the crux of it, okay? Because when I measure vibration, I can determine sag. And sag is basically how much is this line drooping. And from sag, I can calculate the mean conductor temperature, not a spot temperature. You might think, oh, the best way to measure temperature, put a thermometer inside that box. No, that's just going to measure one little hotspot at one little location. That's not what I need. I need to know the temperature of that entire line. Okay, so this gives me the sag measurement, gives me a much better measurement of the temperature across the entire line. I also measure the vibrations, and those vibrations, which we'll talk about, it gives me a way of measuring speed very, very accurately. And all of this feeds into dynamic line rating. So as I mentioned here, sag comes in, and using all of these lovely coefficients, which I'm not going to talk about, I can convert sag to temperature, and we can measure sag from these vibrations down to 20 centimeters worth of error. And we can get a very good measurement of the temperature of the line. In terms of wind, we do something very clever as well. For low wind speeds, the cable's hardly moving, okay? So we use a thing called the Struhol equation. I can hardly say that. And essentially, when the wind passes over the conductor, we get a couple of vortices behind it, which vibrate the sensor, causes pressure differences, and we get vibrations on the conductor. So below 2 meters per second, we can measure it with that. And at high wind speeds, the conductor actually gets pushed aside. So we can measure the equivalent swing angle. And that swing angle is then used to calculate wind. So if I show, I don't have the picture of it, but essentially using those two methodologies, we're able to measure wind very, very accurately. So as I mentioned, we need the conductor temperature, we need to know the wind speed, and from that and other models, we can essentially get the ampacity, which is the amounts of current I can push through the line. I can take the weather measurements, line measurements. I have algorithms in terms of the IEEE models, and I've also got forecasted weather data. So I've got forecasted weather data from third-party weather providers. And I can then forecast, not only tell you what's happening right now, I can tell you what's happening tomorrow. Now, what's interesting is out of all weather forecasts, ambient temperature is the easiest to forecast. A harder one is to forecast cloud cover and rain. And even harder than that is to forecast wind. Those are areas that are very, very difficult to forecast. And particularly with lines, we're not looking for wind at one particular location. We're looking for wind at the height of the conductor and wind that is perpendicular to the conductor. So it's not only wind, it's also wind, well, not wind speed, it's also wind direction. We are able to use our sensors to actually correct the weather forecasts on this area so we can get way better forecasts of wind. And the thing with dynamic line rating is, yes, it's useful to know where you are today, what's happening right now. Can I push some extra megawatts through the line? But it's more important to know what's going to happen in a few hours. Because when I need to get some megawatts onto the line or into my power system, normally I have to arrange that ahead of time. Even better if I can predict what's going to happen tomorrow. So I can start speaking to the power stations today to make sure it goes online. Over here, you're looking at an example. This is just a picture of our HMI showing a static line rating, forecasted line rating, 24-hour ahead, 1 hour ahead in blue, and then the actual dynamic line rating in green, as well as the load. So that's what it looks like in our system. And I'm going to conclude here. I think we've probably spoken enough about it. Fundamentally, we've got congestion costs. Congestion costs are the cost of electricity that increases locationally because we're trying to get power from one area to another. They are exceptionally high, hundreds of millions per annum per country, okay? And they're typically paid for by the consumer, by you and me. So if we want renewables, but we also want cheap electricity, trust me, that's not a bad thing to ask for. Well, this is a problem. This is a problem we need to solve. And dynamic line ratings help. Traditional line ratings are conservative. Line ratings are always based on weather because it's how much cooling am I getting from the weather conditions. But which weather do you use? Do you use the worst case weather, or do you use real-time weather? Do you use weather from a weather station, or do you use weather from a sensor that's directly mounted on the line? Dynamic line rating uses sensors that are directly mounted on the line. They're accurate. They use real-time weather. It makes the line rating far less conservative, takes away the guesswork, produces up to 40% extra capacity gain at around 1% of the cost of building new lines. So 1% is nothing compared to the cost of those new lines. But on top of all of this, I'm talking to young engineers. It uses some pretty cool tech. Inside that box, we've got power electronics, we've got radio electronics, we have got high voltage corona tests, we've got power engineering, understanding capacity and market engineering to understand how much money can be made from these constraints. We've got data science in terms of machine learning models to understand forecasts. We've got a lot of very intelligent engineering that goes into this, that all brings it together and adds value to the world, both I mean, people who don't understand anything about lines absolutely still have to pay for electricity every day. And these solutions are going to affect every single person's electricity bill. Thank you very much. I'm not sure if we're going to have questions at all, but if you want to get in touch, please do. And happy to answer any questions you have.
Great. Thank you for your presentation. We have one question that we got from one of our friends, and
Yep.
it goes, how do you process a lot of data which come from measurement results, and which learning algorithm do you use for this job?
Asking the wrong guy. Yeah, so you're asking very technical questions. So in terms of sensors, in terms of the actual data, so as I mentioned, we've got the vibration sensors. So our vibration sensors are measuring in 3 dimensions. And those 3 dimensions, we're measuring at about 200 hertz. So 200 hertz worth of data points coming directly from that box that's sitting on the line. We've also got third-party weather data coming in. So that's typical weather data, like, is the sun going to shine? So what's the temperature, max temperature, min temperature, wind speed, wind direction, all of that. So we've got two data sources. From the vibrations, we derive data. So we've got equations that turn vibrations into sag, sag to temperature. We've got vibrations that get converted into wind, like I explained. So those are all your data sets. You then have, as I say, 2 points of comparison. You've got wind from the sensor, which is highly, highly accurate, but it's real time. And then you've got forecasted and real-time wind from the weather provider, as well as solar radiation, mean temperature, and a bunch of models that can convert one to the other. In terms of machine learning, that's all you need, right? You need 2 points, so you can say this is my input and my output. So if this is my input, this is what my output would be. So if tomorrow is going to be sunny, if it's going to be rainy, if it's going to be this time of the year, those are like my inputs. What is the wind going to be? We can do that with the sensor. We can do that with the weather provider. And essentially what we're doing in this particular case, we're taking the wind from the weather provider, the wind from the sensor, and we're essentially putting higher weight on the sensor because it is a direct measurement, and we're correcting the wind forecast. So fundamentally, and what do you use for training? Well, you wait for it to become reality. So you forecast a day ahead. If you wait a day, that becomes now reality, and then you've instantly got an error. Once you have that error, your machine learning is just going to reduce that error. In terms of what model are you using, regression, neural network, I have no idea. Honestly, I don't. Too deep for me. But there's a million different data techniques that you could use to solve that problem.
Thank you for both of you for being with us today. It was a pleasure having you, talking with you, and listening to your ideas, your presentations. And after the break at 4:30, we will continue with our next guest. Thank you for being with us.
Thank you. Really appreciate it. Bye now.
Bye. Hello, Mr. Torres, can you hear me?
Yes, I can hear you now.
Welcome, and let me introduce you to our participants. Last but not least, pardon my pronunciation, but Jose Luis Rueda Torres, Secretary of IEEE Power and Engineering Society, will be giving his speech about development of multi-energy system in the North Sea. And let me, oh, you can do it, okay. You can start when you are ready.
All right. So let me just set this up. Okay. Thank you very much for the kind invitation for this short talk. I am very happy and delighted to support this initiative. My topic is normally resilience of energy systems, covering stability and the reliability part of resiliency. And today I will speak about these two topics a bit from the point of view of the development of multi-energy systems in the case of the North Sea. So as I say, my professorship is about resilient sustainable energy systems. I am associate professor at the Delft University of Technology in the Netherlands. My research teams work on resilient, and as we see here at the bottom of the slide, I do research on reliability, which is the performance of energy systems or integrated energy systems, the electricity system and gas, for instance, in time frames in the order of minutes, hours, days, weeks, and so on. Stability is more looking at the instantaneous time response, looking at how robust, for instance, the natural response of these systems or the control systems will react when there are disturbances like outages of components like plants or short circuits and things like that. This means studying performance in a sub-second time scale to look at the reaction of the control systems. What is special with the offshore energy systems and in general the energy systems of the future, thinking of its complete power supply from sustainable, clean, renewable energy sources? Some people call it net zero or clean energy. There are different terms depending on what is the aspect of concern. So let's think of a system without any of the conventional power plants like thermal power plants, but mainly renewables, which are decoupled by what is called power electronic converters. So we are dealing with a completely new system from the physical point of view, which means it has different dynamics. So we could quickly oscillate and have critical oscillations that are unknown. So how do they start? How do they propagate? How many of these oscillations can occur simultaneously? These are different kind of unsolved questions which do not have any concrete answer currently from scientific and also practical point of view. And secondly, we cannot study them properly and unveil their physical roots with the knowledge we have developed, because all the theory we have in terms of conceptual definitions, in terms of equations or mathematical representation of the system, physics related aspects, all is rooted to the conventional system, which was presented by the conventional power plant with synchronous generators. So it's a slow system, the old one, for which we have a lot of advanced tools, but the new one is a very fast system that has complex and unknown dynamics. Another thing is that it's a system that's subjected to lots of fluctuations or variations because of the highly random nature, stochastic mix random, more or less, of the different power plants like wind, solar, also of the consumers who are more active now through the markets to buy or sell energy, for instance. And this means we also need to redefine the way we do control in the system to be more adaptive and to properly address all these complex physical phenomena, which is also varying over time due to the random nature of the power exchanges. So this is the main thing in a nutshell. So designing a new system for which we cannot study property dynamics with the current knowledge. What a beautiful challenge. And secondly, we need to define new ways of controlling it and making it robust against any variation, because currently any systems that we have in any country is so resilient that, for instance, the reliability is more or less almost 100%. For instance, in the Netherlands, we have 99.999, something like that, which means in the worst case, we might expect maximum like 20 minutes, half an hour interruption anywhere in the system, which is very highly robust, reliable system. And stability is resiliency to disturbances. So we do not have blackouts. We do not have incidents in our systems every day or every hour. This means because we have properly designed controls. And as I said, these were designed for the classical system without renewables, without stochastic behavior, and so on. So this is more or less what is the main challenge. And now I will give some examples of ongoing studies that we have conducted in my team to highlight how these challenges will look like when we monitor some system responses. And at the end, I will close with some remarks on reflections on some findings so far and the way forward in the next stage of my research. So first, the pooling. In my team, we work in we call it Electrical Sustainable Power Lab. It's a brand new lab we have inaugurated in Delft, in which we have, as we see here in this figure, we place together, we meet together with different research teams did by the different professors. So for instance, some work on high voltage technologies, others in renewable power generation like wind or solar, we see here, others working on other developments like electric vehicles and the aggregation, or battery storage, as we see here, or power to gas conversion and things like that. And my team works mainly here, you see here, with real-time digital simulator, which can be interfaces to any hardware through some physical amplifiers that allow us to scale up or down currents and voltages. So this is a very beautiful development, because now we can really go into more detailed modeling. So with this simulator, we can really model in all details possible the electrical and other various systems with respect to the interaction with the electrical system, and we can interface with actual hardware to have it in the loop. In that way, we can test many things like different conceptual designs of different technologies that could be deployed, for instance, to harvest more renewable energy or to make a consumer more response and things like that. And in that way, we can also test the controllers. So in a nutshell, then, with this beautiful playground is where then the researchers in my team can investigate deeply what are new theories needed and what are the new control principles needed to safeguard the resiliency, that means the reliability and the stability of the future energy systems. So it's important because this is the tool chain, and this was used, for instance, to or is being used to study in the first stage of a long-term research program, 5 and 10 year research program, different aspects of the developments in the North Sea. You might have heard or might read about the North Sea developments in the European Union. We have goals that are defined already. One is like to attempt to be climate neutral by the year 2050. The power sector means should be substantially and, if possible, fully decarbonized, means that no fossil fuels are used for production, for instance, and will reduce any possible source of CO2 emission to the minimum, if possible, zero. And then to achieve these two goals, regional cooperation is essential, because our system, you see here in this example, I am moving my pointer here, is connected with the rest of Europe with the interconnected European system. So many developments we do offshore in our coastal area is going to have an interaction through our electrical network with the rest of Europe. Same happens with other systems or offshore systems in the North Sea, like for instance the parts that are developed for Germany in this example, or for Norway, or for Denmark, UK, Belgium, and so on. So then this means we should start at some point, which is meaning, for instance, what if we start adding more offshore wind power generation? Because theoretically we can have here up to 300 gigawatt, and for the Dutch system is more or less the portion around 60 gigawatt that we could theoretically install more or less in this part of the North Sea. And that big, bulky generation is not going to be built in a single run. So one possible approach is to use this so-called hub and spoke concept, which means we do it in a modular way. So we modularize the development. So we have, for instance, a system of 1 or 2 gigawatt here, and then it can connect with other systems of similar size and impossible or high size. We will see that over time, how fast we can work with developing the proper technologies and the proper control systems to ensure both reliability and stability. So this is just a very short overview, more or less, how the growth of energy consumption is expected to grow more or less with some different, this is like an average more or less of different projections done across the Europe. So from until year 2050, more or less, in which we expect more or less that more or less 40% of the generated electrical energy could be used for pure electrical consumption, and 60% could be used for electrification and application in other energy sectors, like for instance, the production of gas or transportation or heating. So this means the sort of coupling, like between electrical energy system and other energy sectors, is a key, because through this coupling, this means the other systems can support the electrical system, sometimes by consuming more, sometimes by consuming less. For instance, we can help the electrical system to be more resilient. This is important because in the future system, we have a fundamental difference that the consumers and storage devices can have a role in helping to balance the generation and demand of energy. Currently, it's just consumers do whatever they want and generation has to follow these variations. But in a new system, we both cooperate. This can unlock many opportunities to have this balancing task completely taken over from what is happening now in a conventional system. So there's a huge remark from the sector coupling, and there are many expectations around that. There are many different programs, like for hydrogen, for heating, and so on. This is just a short overview of the statistics of projects that have been completed, projects that are going to be added till 2030 or 2050. You see, in our coastal area in the Netherlands. So example values of the expected demand by 2030 and 2050, we have in over terawatt hours. The considered energy consumption, you see, is going to grow significantly. And then we would like to achieve higher reduction, especially towards 2050. And then the expected generation, especially in the North Sea, is expected to grow like up to 10 gigawatts by year 2030, and 3 to 4 times in year 2050. To do that, we really need to speed up with the knowledge, with the progress in the knowledge. That means in terms of the tools, we need to do studies to generate such a gigantic system, and also the control principles to safeguard reliability and stability. So example of one possible module that, as I say, could be of 2 gigawatt size in some different locations around the coastal area of the Netherlands. These are examples of how such modular developments could happen in future. The architecture for such development is still being under studies, technical studies at the industry or research studies at the research institutions. There's some examples of possible connections, trying to do interconnections country by country. This is more or less what is happening nowadays, or trying to do something that is more around an individual or a particular offshore electrical network in the North Sea, in which the countries can just connect to it and then exchange energy through this network, which will have very big, bulky power plants for renewable energy based. What is the challenge of such offshore systems? As we see here, this is another example. So we have these modular developments. We indicated that we might have even some electrolyzers located offshore to try to harvest electrical energy generated by the wind, and then send it through pipelines, for instance, submarine pipelines to the shore with hydrogen gas to storage facilities for deploying it at a different time scale, especially towards down seasonality. Why is the challenge to develop these modules and interconnected? And is because we can claim that they are clean. They could even have some economic development. However, in terms of stability and control, this is so challenging, especially when we look at phenomena in the micro to milliseconds time scale. Many researchers have been done to cover other aspects that are also very important, like the balancing in several minutes to hours, the storage, how to build facilities or to monitor, and how to manage long-term, like different hours, days, or weeks. This is very densely investigated currently. However, we need to go we need to start going into the fundamentals of physics and mathematical and control point of view to cover dynamic stability in a microsecond time scale. Because we don't have the facilities that are going to be connected, that the wind turbines or the responsive electrolyzers to produce hydrogen gas, for instance, we cannot design proper control systems and we cannot safeguard this dynamic stability. This is an example of the importance of such research methods. There is a project in which I worked and was closed last year with the TSO 2020 project. We have here the website, so tso2020.eu. You can type this in your browser and then you will see all the deliverables, all the findings, and a lot of material, including videos and so on. In a nutshell, what was done in this project is that I designed with my team new controllers that are attached to electrolyzers. Normally, electrolyzers are passive. Until now, most of the passive components, they just have some sort of power electronic converter, like a rectifier, which is connected to another converter, and then the current, and then being used to produce hydrogen gas, utilizing electricity with water to do the decomposition, and we get hydrogen gas. This is like passive, just like to use it to produce hydrogen, and it's doing almost nothing. However, in this project, the electrical power was redesigned to have a fast active power regulation, FAPR in the abbreviation, which basically means we completely redesigned the electrical interface with the electrical system, and then we could make it responsive to fluctuations of the observed system frequency. Frequency is a parameter that reflects the balance of the active power. The megawatts, for instance, or gigawatts that are being produced should equal the megawatts or gigawatts that are being consumed at any time. The area fluctuation in this is going to be observed in the frequency. You probably have seen that most of the appliances here in Europe have 50 hertz, the same frequency. There's an imbalance between the generation, consumption, and losses. Then this frequency will start to vary, like in this example figure. And then if there is, for instance, less generation of electrical energy than consumption, this frequency will tend to decrease. And if you have decrease it or no conventional plants, this will go very steeply to very unacceptable values. And then if you know the stop here in this point, this is the maximum frequency deviation downwards in this case, the system will have actuation of the protection devices. We will start as connected more generation units, and we start having cascading loss or more loss of generation, and we start having blackouts. So to prevent that, then I designed a control system to make these electrolyzers responsive, and then they could intervene and help to mitigate this abrupt fall of the frequency because of less generation on demand, to arrest it to an acceptable maximum deviation, and then reducing also the margin that is needed to restore it later on in a longer time scale with other control actions. So this is a huge finding, because normally these kind of devices, which also happens with other consumers, are normally said to be a troublemaker, so a part of the problem. But we add new control principles to it, we can make it responsive, and instead of being a troublemaker, could be a problem solver. So this is an example of one fundamental change, a radical change we have to do also at consumption side. This is why we're working more and more with integration with other energy systems, looking at how to lock their responsiveness in terms of control to ensure both resiliency and reliability and stability, two important parts of resilience. This is an example. We did a study how to apply this device in a model of the north of the Netherlands, where we expect to have in the near future electrolysis plants like from 300 megawatt or even or gigawatt. So I did a study, and then we did field measurements with a pilot project. We started an electrolyzer and we tested the response. And with this, we use it to validate, for instance, how the demand could be, the consumption could be increased on one side or could be decreased. And this figure shows the continuous line is the response of the models we develop in the lab. I showed in the previous slide, we have a lab with a supercomputer in which we can create detailed models. And these models are recreated with these responses with the continuous line, and the dotted line was actual measurements with new technologies. So we see that we can have very close behavior, which is very, very, very important. This highlights the importance that a sufficiently detailed model is capable to properly capture the responses of what could be possible new technologies. This is very important in the development of new systems, because this way we can anticipate problems earlier and the risk possible unexpected behaviors that could happen when these new facilities come into place. So we are trying to unlock possibilities also to anticipate problems and have a better representation of these problems with the modeling and simulation. For this, more detailed models are important, and this is why we have the supercomputer. Next stage will be to redevelop the analytical framework with formulas within cause and effect. This is part of the next stage. This is an illustration of how important it is to have our interface. So here we have an electrolyzer connected here with an electrical interface. This other device represents the electrical source, trying to emulate what will be electrical plant here in the system. The whole system is modeled in full details in the supercomputer. So this means every simulated second takes 1 second of simulation. So we don't have slow simulation. We was the old practice. We built a model and we have to simulate 1 second, like in 1 hour or 2 hours. Now we can simulate it within a second. This is why we need a supercomputer. So then we added the control systems. We decided with my team to control this electrolyzer, the electrical part that was redesigned. And this will be the current technology that is not support. That happens, as I indicated before, the frequency falls down, meaning that we have problems with balancing the system. If we have one type of established frequency power frequency control, we could bound it to some minimum value, and that this means we are helping the system already to prevent the collapse because of too high deviation. We could add another approach that we define to have a somewhat different characteristic, more nonlinear, and we have improved the response even at an earlier stage. The steepness of the deviation is less critical. And if we add even a different one, we could try to improve a bit further. You see how important it is to have the opportunity to develop a control strategy and program it already in digital control. This is a digital controller, and test it at laboratory scale. Even if it is a prototype that is 10 times, 100 times smaller than the real device, it's already very valuable because we can test a lot and recalibrate it and tune it before going to the field test. So this is a very valuable progress. We don't have the coupled studies. In the past, we did everything offline, as I say. It took longer. We designed everything, remained theoretical, and then some basic testing at lab scale. And then we don't have any warranties if this is going to be a good match later on or fully the risk, something will go to field assurance. So this is a significant progress. And there are some learnings from the TSO 2020 project that with the hydrogen CSA, we can use the response of the electrolyzers to safeguard the resilience of the system. Of course, there are more parameters that we are investigating, like the rating of these devices, where they are located in the system. We can optimize the controller even more. For that, I am working on new theories. And then how to do that with the least computational effort is one of the key challenges. And then how we can apply these control principles to other developments, like for instance, electric vehicle aggregation or battery storage and so on, but has to be still further research. And how we deploy that in the offshore systems like in Dorsey is also a big question. So it's not that I just take what the same for electrolyzer and apply it there. it is not like that because the offshore system has different characteristics and we have to investigate that. First understand and then see how we can tailor this development. And to conclude my part, I will just summarize quickly in 2-3 minutes the ongoing work on the offshore energy systems. To develop these studies, we need to go step by step. And one of these is to have good models, as I showed you before for the electrolyzer. I showed you that we could even validate it with field measurements and have very high resolution in the response. Now for the offshore systems, we cannot do that because we still have to construct. However, we are ready to start working in models. So on one part was to develop representations for the offshore wind plants. This is an example of what could be done with the current practice, traditional with offline simulation. This is an example commercial tool. And then we need to go for detailed representation with the our supercomputer real-time digital simulation. We can model that and we can use that to recalibrate the models that are available, for instance, for our operators or developments, which have more simplified representation. To tune simplified representation against the entire representation is one important step already. So this way we can try to compare different studies, especially those who look at longer time scale, like minutes to hours, try to connect findings with what we find when we do studies at a second or sub-second, less than a second time scale. So then we need to align the way we do these studies, because this is important to see how we compare solutions that are discovered or problems that are discovered in a sub-second, what will be needed later in a transition in the longer time scale. This is also an important aspect. So this means the simplified model and the model should be able to have somewhat resemble dynamic patterns when we measure physical quantities like voltages or currents. And here we have an example of measure voltage with or simulated voltage with the detailed model, the green one, and the simplified model with red one. It will do proper calibration as we have done with my team. We have high resemblance as we can see for the voltage. And we can see the differences in the modeling are more appreciable when we go to the curves in this case. So we have here with blue, for the currents, the one with the very detailed model, one with red with the simplified model. You see, simplified model has some substantial differences, which even if we try to tune to the best, they cannot be reproduced, meaning that the level of simplification is not suitable to use that model for something that should be really looking properly at the sub-second time scale. So we cannot use the simplified model like in red to do a sanity check for what should be happening in the real system, which is more reflected with the response in blue. So in this case, for instance, we have a very important remark that the tail modeling is a key. How to do that with reduced computing time, we are working on that. So then we added these detailed models or the simplified to build an example system of the 2 gigawatt, the model of the offshore. This is one interconnected to the onshore system with 1 gigawatt. This is another one. And then we have the number of wind farms connected offshore in the collection system. This is one example configuration that could happen, and then we see a simulation of its energization or the course. And so we see the simulation of electrical fault that causes the loss of a wind farm, and then the system starts to have some oscillatory response. And if we have some new control systems as the ones we have designed, we can manage to stabilize it and have it properly working. In another presentation or in a future event, maybe I can talk a bit more about these control systems. However, here we're illustrated, but with a proper design control system, we can manage to stabilize the system. With existing methods, with most of them, this will go down and will collapse. And this is the last part. Then addition of electrolyzers at turbine level in each wind turbine in the wind farm, or in a centralized location in the collection system where all wind farms are located. It's a big question being in discussion. What is the best, to have all distributed or try to centralize? But we are doing some ongoing research to compare both options, and we can see here that it has some pros and cons depending on the location. We have here a summary of these findings. So if located at a centralized local part, we can have some support for balancing the whole system. But however, if we have some power loss because of failures in the wind farm and one of the wind farms, then we will lose some energy. We cannot harvest it to the maximum. So that cannot there is a disadvantage. For instance, if you have it distributed, then we will still harvest more renewable energy and will reduce the loss of renewable energy. However, then we need to think into logistics to keep the operation and maintenance of such facilities, and also more special control system we added on the turbine level. So these are some example challenges that we are unveiling now with different options for the design, and then we need to see what it means in terms of the characteristics of the control systems that we have. And to close, I show some pictures of our lab, different places. So you have some flavor. This is the high voltage part. This is one of the cores that go to the real-time digital simulation. And here we have the supercomputer, the real-time digital simulation with some super fast processors to study with more details, power electronic converters, some hardware here like relay protection relays. And here on the top right, we have our special control room, which is a replica or is an evaluation of what will be a real control room for our future energy systems with all the information technologies that are needed for information processing monitoring. Here we can also do, we are doing research on cyber attacks, for instance. So that's it basically. Thank you very much for your kind attention. I don't know if there is something planned for questions. I can answer a couple of questions before I leave because I have to move to our next meeting.
We have one question that I would like to ask you. It came from our YouTube chat, and it says, with your level of expertise, do you believe that European expectation from carbon neutrality is possible with so little time?
Could you repeat a bit the question? I didn't understand what is the question about.
Yes, with your level of expertise, do you believe that the European expectation for carbon neutrality is possible with so little time?
Yeah, we are leading a lot in the development of technologies for renewable energy, especially one of the whole chain, not only mainly wind, but also solar. And then we are working a lot on power electronics. So we have a good level in terms of research and development, and we are progressing more as a different places across Europe with this development. So I am not the only one working with like real-time digital simulation or power hardware in the loop. So we are converging. What is very important to highlight is the valuable support we're having in the different countries, but also with the European Union funding our researchers to go faster with the acquisition of necessary equipment. As you saw, going deeper in modeling is one key. Another is interfacing with hardware. This is quite expensive. So building such a lab is several millions of euros. And for that, valuable support by society and government is important. So both academicians, scientists, and experts working in the field, building and operating the systems, we can work together, join force, and in this way can go faster. I think this is already happening, and it's a very valuable cooperations that will boost the way to generate the new knowledge. As I told you, we need new methods, we need new tools, and we are really working really hard in quite some projects as well.
Okay. Thank you, Mr. Torres, for being here with us today, for answering our questions. We came to the end of our summit. We want to present our special thanks to all of our speakers and participants for being with us today to discuss smart grids. And we, as Electrical Engineering Club, wish you all a nice rest of your day.
Okay, thank you. Bye.
Thank you. Bye.